Last section we talked about finding the rate for a particular reactant and talking about how quickly it's disappearing, and we also talked about finding the rate for a product and how quickly it's appearing. We talked about average rates, doing the change in concentration over time, as well as instantaneous rates where we're finding the slope of that tangent line. Well, today we're going to talk about the rate of the overall reaction. And the rate of the overall reaction is shown by something called the rate law. And the rate law is written as an expression, and I'm circling it here. If you were asked to write a rate law, you would be writing something like you see here. The rate of a particular reaction is equal to K. That K is not constant. And the rate constant is specific to a specific reaction at a certain temperature. For example, the decomposition of peroxide, just to pick something random, the decomposition of sodium peroxide at 25 degrees Celsius has a specific rate constant. So that rate constant goes with that reaction. And as long as you're carrying out that reaction at that temperature, it will have the exact same rate constant. So when you're writing a rate law, you just include K. And then they may ask you to go back and calculate K later on, or they may give it to you. But in the rate law, you're not including the number. You're just including that letter K. If you remember back to equilibrium when we were asked to write expressions, writing a rate law is very similar to that. So you're not really putting in any numbers. You're just writing the law. So the rate law shows the rate for the overall reaction. And again, it is rate equals K. And then you include your reactants in brackets to show that we're talking about their concentrations. The concentrations of the products have nothing to do with how fast the reaction goes. It is only the reactants and their concentration that affect how fast the reaction goes. Remember here, we're assuming that these reactions are moving forward, and we're talking about the speed at which they do so. So the rate of the forward reaction equals K, the concentration of each reactant raised to, and this is not its coefficient, but these exponents are what are called the order. So the order in terms of A and the order in terms of B. So again, just to note, this is not their coefficient, or not necessarily their coefficient. If it turns out to be the same thing as the coefficient, it is just happenstance, okay? It is not the norm. So, to write a rate law, we're talking about the rate for the entire reaction. This is not the rate for A, or the rate for B, or the rate for C, or the rate for D. This is the rate for the reaction as a whole. It is equal to the rate constant for that reaction times the concentration of your reactants raised to their orders. All right, so we'll break that down further. Rate law. These orders cannot be predicted from the balanced equation. So you cannot look at a balanced equation and say, oh, the coefficient is 2, so the order must be 2. Right? That is not the way it works. These are found only through experimental data. So the only way to know the order is to look at experimental data or have someone else look at experimental data and tell you the order. We cannot look at the balanced equation. The order may be 0, first order, or second order. And we'll talk about what that means, but those are the only choices that we have. So our exponents in our rate law can either be 0, 1, or 2. Now overall, if you have like 2 reactants and each one has an order, then your order could be bigger than that. But for each reactant, its order can only be 0, 1, or 2. And I know at this point it probably sounds like I'm talking in a different language, but just bear with me as we build our knowledge here. Your order is your exponent in your rate law, and the only choices are 0, 1, and 2. There are such things as half order or fractional orders. They are not tested. Okay, they are rare and they are not tested, so we're not going to worry about them. So we're going to pretend that we're in our little high school chemistry world. Only orders that we have are 0, 1, and 2. Alright, so now let's break that down a little bit further. Let's talk about zero order reaction. If you have a reactant that is zero order, what that means is that it is not determining at all the speed of the reaction. It has no effect on the speed of the reaction. See if I can type here. No effect on the speed of the reaction. Alright, I'm not sure if that's effect or anything. But if we change the concentration of whatever we're talking about, it does not affect the rate. For example, if you have A as a reactant and you take that reaction and you run it again with double the concentration of A, the rate will not change if A is zero order. Because anything raised to the zero power is 1, right? Anything raised to zero power is 1. So no matter what you change A to, changing that does not affect the rate of the reaction. This is very common when you have a solid species in your reaction and you change its concentration, because you really can't change the concentration of a solid, right? So changing that concentration may not affect the rate of the reaction. All right, again, just bear with me as we build here. This is an example of a zero order reaction over time. So the concentration of that species over time is going to be a straight line if it's a zero order reaction. Because the rate, right, the slope, does not change as the concentration changes. Remember back when we looked at the concentration versus time, actually let me flip back. These graphs, see how these are not straight lines? So over time, as the concentration of this thing changes over time, it's not a straight line, right? Our rate is different here than it is here, and then the rate's different here. The tangent line changes, right? But if it's zero order, over time, the concentration is changing, but that tangent line, that slope, that rate, stays exactly the same. Because no matter the concentration of this species, the rate is not affected. So the rate, which note here, is our slope, it does not change as our concentration changes if we are zero order. So concentration versus time is a straight line only for zero order reactions. So if you have concentration on your Y and time on your X and you get a straight line, then you know it's zero order. Because normally we would see a curve here, or this way if it's on the cross. Alright, first order. First order, the text box again. If something is first order, then changing its concentration has a direct effect on the rate. Any reactant that is first order will have a direct effect on the rate when you change its concentration. For example, if you double the concentration of that species, it will double the rate of the reaction. So doubling the concentration doubles the rate. The same thing would be true. If you triple the concentration, you will triple the rate. If you half the concentration, you will half the rate. Whatever you do to the concentration of that species, the exact same thing happens to the rate if it is first order. Okay? Whatever you do to that species, the exact same thing happens to the rate as long as it is first order. Because you have a 1 for your exponent. because your order is your exponent, right? So if you triple whatever's inside here and you raise it to the first power, it's going to triple this rate. Remember, this k is a constant. So if you multiply this times 3, you're multiplying the rate times 3. If you half it, you're halving the rate because your k is not going to change. So first order reactants have a direct effect on the rate. Second order reactions have a squared effect on the rate. So if you double a second order reactant, it's going to quadruple the rate. Okay, does that make sense? Because 2 squared is 4. So if you double the concentration, then you're going to multiply your rate by 4. If you half your concentration, what's half squared? You're going to fourth your rate. If you triple your concentration, you're going to multiply your rate by 9. If you quadruple your concentration, what's 4 squared? You're going to be multiplying your rate by 16. So whatever you do to that species, if it is second order, then that effect squared happens to the rate. Okay? And this is important because if we want to make a reaction run faster, we want to do so as efficiently as possible. So let's say I have this reaction and I really want it to go faster, but one of my reactants is 0 order. Well, I don't want to mess with it because it has no effect on the rate. Then one of my reactants is first order and the other one's second order. If I mess with the reactant that's second order, that's going to have the biggest effect on my rate. Because whatever I do to that reactant, it actually is squared in terms of my rate. Right? So that's what 0, first, and second order means in terms of our reactant. The overall order for a reaction is found by just adding up the exponents of your individual reactants. So if you have 2 reactants, and let's say the first one's first order and the second one's first order, then you would just say 1 plus 1 is 2. So the whole reaction is second order. But if your first one is second order and your second one is first order, 2 plus 1 is 3. So the whole thing is third order. If they're both second order, 2 plus 2 is 4, the whole thing is fourth order. If you have another reactant, let's say there's 3 reactants in this particular one, then you would add up all 3 coefficients to find your overall order. So overall order is simple, just add up the orders from the other reactant. Right? Now our rate constant K. So remember, our rate law is rate equals K, which is our rate constant, times our reactant, or reactants, raised to their order. So let's say the order is 0. So that would be rate equals K, your reactant, raised to the 0 order. If it's 0 order, this goes away, right? So you just have rate equals K. In that case, the units for K would be molarity over time. And they use seconds for time here, but really your time could be minutes or hours or days. It just depends on how slow your reaction is. So watch out, this won't always be seconds. If your order is 1, and this is talking about the overall order for the reaction, and here we're just using 1 reactant, but you could have multiple, but if the overall order is 1, the units for K are 1 over time, or 1 over seconds, or seconds to the negative 1. This negative 1 means that it's on the bottom of a fraction. If your order is 2 overall, like K equals A to the second, then your units would be 1 over molarity on the bottom now, and seconds still on the bottom. And then if your overall order is 3, which it couldn't be 3 for just A, they're just using this as an example. So this would be if A was 2 and B was 1, for example. Your overall is 3. Then this would be the units for K. Right? They ask you for the units on K a lot. So this table is just helping you to figure them out. If you know your overall order, then you can figure out your units on K. The key is that the units on K are equal to 1 over molarity to the order minus 1. So if your order is 1, 1 minus 1 is 0, right? So that's why there's no molarity in that unit. So it's 1 over molarity to the order minus 1 times time. And I'll put seconds, but remember that could be anything, minutes, hours, whatever. Okay, this is your overall units for K. And then here, they figured it out for each particular order. So we'll come back to that when we're calculating K. Alright, so right now we're just putting a bunch of little pieces together. We've talked about what it means to be 0 order, first order, second order, and overall order. And here we're looking at how the units of K would be affected in those particular orders. Alright, now let's do an example. Hopefully some of this will start to make sense in this example. We have a particular reaction that we want to know the rate law for. And this reaction has two reactants, NO and H2. And we're going to do 3 experiments to look at how the rate is affected by different concentrations of these reactants. So in the first reaction or experiment, we start out with 0.20 molarity for our nitrous oxide, or NO, and 0.3 for our hydrogen. They just pick these random values, okay? And then they measure the rate, and they find that it's 0.900 molarity per second. This is always your unit for rate, molarity per time. And again, that could be different times. This one moves pretty fast, so they do per second. Right. Then they run the experiment again, and they change one variable. Remember, that's a key to experimental design. When we run our second experiment, we don't want to just go pick random numbers. We want to change one thing. So what they did is they changed the NO value. And you can see here that I have the amount of NO that they started with. Because they want to know, what effect does this have on my rate? So I'm going to half my NO, okay, 1/2, and then we're going to keep the H2 the same, which is important, right? We don't want to go changing everything. So the H2 remains constant here. And then the rate, what does it do? The rate, we're going to have to pull out our calculator, but the rate seems to be divided by, anyone see that number? The rate actually gets divided by 4. So it is 1/4 now of what it was before. So our concentration is 1/2 of what it was before. Right? So, sorry for that interruption, but the concentration was halved and the rate was 4th, right? Or divided by 4. So let's think about that in terms of order. Did it have no effect, a direct effect, or a squared effect on the rate? Well, we know it had some effect, right? Because the rate changed when the concentration changed. And although the concentration was halved, the rate was not halved. Instead, the rate was divided by 4. So that is a squared effect on the rate. So that tells me that the order for this NO is 1. The order with respect to the NO is the first order. All right, now let's look at experiment 2 compared to experiment 3. So when they move from experiment 2 to experiment 3, they keep the concentration of NO the same, but they change the concentration of the hydrogen this time. And that's good because now we can study the hydrogen by keeping the NO constant. What did they do to the hydrogen's concentration here? Well, they took 2/3 of it, right? 0.2 is 2/3 of 0.3. If you're not sure what they did, you can just do 0.2 divided by 0.3 on your calculator, and you'll know that it is 0.66 or 0.67 if we round to sig figs. Sorry, it's not writing well today. But it's 2/3 or 0.6. All right, then what happened to the rate? Was there no effect? That would be 0 order. Was it a direct effect? Whatever happened to the concentration happened to the rate? Or was it a squared effect? So if we look at this relationship here, 0.15 is also 2/3 of 0.225. So here we have 2/3 of our concentration, and that's also 2/3 of our rate, so that is first order. I apologize, guys. I made a mistake on this NO. Thank you if you caught that. That was a squared effect, right? So that is second order on the NO. I apologize. because the NO was halved while the rate was divided by 4. On the H2, it was 2/3 of the original, and the rate was also 2/3. So those are the same. That's a direct effect first order. So now we could write our rate law. Let's look at how they do that on the next slide. So we found that the first one was second order, and the next one was first order. So our rate law would be rate equals K, just include our rate constant, each of our reactants in brackets, because we're talking about their concentration, and then raised to their order. We got second order for NO and first order for H2, right? So there is our rate law for that expression. So when they ask you to find the rate law, you need to know the order for each of your reactants so that you can put those as exponents. You're going to leave K just as a constant, and then you're just going to write the word rate equals at the beginning. Now I want to go back and show you, because we kind of used what I call table logic when we were looking at this. We said, okay, what happened here? What happened here? What is the relationship? But there is a way to do this using algebra. So I want to show you that way. Some of you will prefer this much better than the table logic, and some of you will use the table logic. Totally up to you. So to find the rate order, what you can do is compare two experiments. So they're using experiment 1 and experiment 2. And they just write the rate law for each one as a fraction. So the rate law for experiment 1 is equal to K times the concentration in experiment 1 raised to some order, the concentration of H2 raised to some order, divided by, and then they do rate 2. Rate 2 equals rate constant, concentration of NO in experiment 2 raised to the order, concentration of H2 in experiment 2 raised to the order. And they just plug in. This is the rate from experiment 1. This is the rate from experiment 2. K is our constant. This is the concentration from experiment 1, concentration from experiment 2, concentration from experiment 1, concentration from experiment 2. Right? And then they're going to see what cancels. This 0.3 on the H2 is going to cancel because it was the same in experiment 1 and 2. K is a constant, so it's going to cancel. Then they divided their rates and got 4. They divided their concentrations and got 2, so now they're able to solve. 2 to what power is 4? And they find that that power is 2, so they can say that must be second order. And that is on the NO, right? Because the H2 was the same here and here, so it canceled. Right? Then they used experiments 2 and 3 and compared those. So you have the rate from 3 and the rate from 2. Now, it does not matter which one you put on the top and the bottom, and they purposefully flip-flop these just to show you that. So you could do 1 over 2, 2 over 1, 3 over 2, 2 over 3. Then they write out their rate law for 3 and divide it by their rate law for 2 and plugging in their numbers. So this time our NO is canceling, and we're left with 2 over 3 with an exponent that we don't know for our H2. And then we do the rate divided, and we got 0.67 equals 0.67 to some power. So what must that power be? That power must be 1. Right? So our order for this one must be 1, which we determined earlier as well using the table logic. So feel free to go back and pause and write down this math and kind of work through it that way if that makes more sense to you. Or go back and re-watch how I use the table so that you can use either table logic or algebra to solve for the rate law. Okay, we'll pick up there on the next video.